We're going to do example 7.5.2. Let x and y be independent random variables with respective density functions f sub x of x and f sub y of y. If we let t be this expression, x minus 3y all squared plus 2, find the expected value of t. The first thing that we might want to do is expand t. So t would be x squared minus 6xy plus 9y squared plus 2. And if we went about this naively, then we might say, well, if x and y are independent, then their joint PDF, f of xy, is the product of the marginals. So it's f sub x times f sub y, which means that we would have 1/5 times 1/4, 1/20th, e to the, and if we use laws of exponents, 1/5 x minus 1/4 y, and this is going to be when x and y are greater than 0 and 0 otherwise. And if we have the joint PDF, then we can integrate to find the expected value using bivariate lotus. So the expected value of t is the expected value of this monstrosity, x squared minus 6xy plus 9y squared plus 2, which is the double integral. And if we just go directly to the support, so from 0 to infinity, because this is improper, this is an unbounded integral, from 0 to infinity of the function, which is this thing, so x squared minus 6xy plus 9y squared plus 2 times the density function, so times 1 over 20 e to the minus 1/5 x minus 1/4 y dy dx, and that is just awful. That is just awful. I would not want to do that integral. And so what is a better method? Better is to recognize, first of all, that these are well-known distributions, and then to use the properties of the expected value. So the better situation here would be to recognize the distributions, and we'll do that in just a second. Recognize the distributions and use the properties of the expected value of e of x. So these are exponential random variables. So x is exponential, and we should recognize that this is the lambda. So x is an exponential random variable with lambda, we'll call it lambda sub x, is equal to 1/5. Y is also an exponential random variable. It's got the same form for the density function, but its lambda is 1/4. So now we know things about the exponential random variable. We reviewed them in a previous section. We know, first of all, the expected value. The expected value of a exponential random variable is 1 over the lambda, and so 1 over 1/5 is 5, which means that the expected value of y is 1 over its lambda, 1 over 1/4 is 4. We also have results about the variance. The variance of an exponential is 1 over the lambda squared. So that gives me 25 for x, and 1 over lambda squared for y gives me 16. So using a little bit of memory work or knowledge about these distributions, about the exponential distributions, and properties of the expected value. So if we take this is still true. So this expected value of t, I'm copy and pasting here, but it's being a little slow, is still the expected value of x squared minus 6xy plus 9y squared plus 2, but we can split this up. So we've just seen by linearity that we can write this as e of x squared minus 6 times e of xy plus 9 times e of y squared plus e of 2. Now there's a couple properties that we can apply right away. So e of x squared, we know x and y are independent, right? That's what we were told up here, that they are independent random variables, and in fact that's what we used when creating the joint PDF. The property of independence can be applied here. We can split that up as a product. So 6 times e of x times e of y. Now this, notice though, x is not independent from x. Obviously it depends quite a bit on itself. So this is not e of x times e of x. We're going to have to think of something else for here. In the same way, 9 times e of y squared, that's not e of y times e of y. E of 2, expected value of a constant, is just that constant. Right, so this, let me write a little note there. This was by independence. Independence. So what we need to do is figure out how to get a handle on these values, and we're going to use the variance. We know the computational formula that v of x is equal to e of x squared minus e of x. So if we want e of x squared and we have the other two things, which incidentally we do, we can solve for it by shoving this over to the other side. So e of x squared is e of x plus v of x. So we're going to write that here. Our e of x squared is going to be e of x plus v of x minus, and we'll just recopy the terms that we already have here, e of x times e of y plus 9 times, and we'll do the same thing for e of y. We'll use this same little trick. So we'll open a bracket here. That's going to be e of y plus v of y, and then plus 2. Now all of these things are values that we have up here. So if we write those out, we've got e of x, which is, oh, and there's a little mistake. There's a little mistake. I hope you were upset at me for it. Let me correct that mistake. E of x squared minus e of x all squared is the computational formula. So that makes this a square and this a square. So now let's get this in the right place. So we've got e of x, which is 5, so 5 squared, plus v of x, which is 25, minus 6 times e of x, which is 5, e of y is 4, plus 9 times, open a bracket, e of y squared, so 4 squared, plus 16, plus 2. And that, we can just crunch the numbers and we'll get 220. So using the properties of the expected value and some prior knowledge about known distributions, which we had to recognize, is a lot better, a lot easier of a solution than trying to crunch through this big old nasty integral, which, while true, right, that certainly does, that is the joint density function, that is the valid expression for it, but this, I think, is the much more efficient way of solving this problem.